We have discussed in the last class about the conservation of linear momentum and rocket propulsion, the theory of rocket propulsion, etc. Today we will discuss about a new concept, which is center of mass and the motion of the center of mass, etc. Okay, so for this, let us consider a system of n particles having masses m1, m2, etc., mn and instantaneous position vectors r1, r2, etc., rn respectively. We are considering a system which having a number of particles, n number of particles, each one having masses like m1, m2, etc., mn, and center of masses like position vectors like r1, r2, etc., rn. The center of mass of the system at this instant is the point whose position vector r is given by. So for such a system, the center of mass whose position vector can be given by the formula mr is equal to m1 r1 plus m2 r2 plus etc. mn rn. Okay. This is capital N, not small n. You might have often tried to balance your notebook or scale or some material on the tip of your finger. So you cannot balance that object in every point of that object. You can balance that object on the tip of your finger only at a particular point of that object, right? And that point is known as the center of mass of that object. Okay, this is the concept of center of mass, and our problem is how to measure the center of mass of any object. That's our problem here. So in order to measure that center of mass point or the position vector of that center of point, we are considering such a system of n particles, and the position vector of that center of mass is given by the formula mr is equal to m1 r1 plus m2 r2 plus etc. mn into rn, where m1, m2, etc., mn are the masses of the particles and r1, r2, etc., rn are the corresponding position vectors. So here on the left side, the capital M is the total mass of the system and m1, m2 are the individual masses. So the total mass can be represented as the sum of individual masses like this m1, m2 plus etc. mn. Okay. So this equation, r can be written as r is equal to this term divided by m, where m is m1 plus m2 plus etc. m into n. So we can write using the summation symbol this equation as the numerator as summation over n is equal to 1 to capital N m small n r small n. Here small n is the dummy index which varying from 1 to capital N, where capital N is the total number of masses present in the or total number of particles present in the system. So this summation index and the this index should be taken care of. Okay. Now this is small n and this is capital N, and the denominator it will be summation over n equal to 1 to n m. So this is the position vector for the center of mass. The summation mn rn is called the first moment of mass for the system. First moment of mass for the system. So for a system of two particles, so this is a system for n particles, and for a system of two particles we can write simply as R is equal to m1r1 plus m2r2 divided by m1 plus m2. Okay, so this is the position vector for a system of two particles. Now if x, y, z are the coordinates of the center of mass, then R is equal to x I cap, y j cap plus z cap. So that suppose this is a three-dimensional system like this. So the coordinates axis are x, y, z. This is a coordinate system representing this. So this is a system in which so this is the coordinate system in which the system is present. So we have to find out the center of mass of the system. For this we have to measure each coordinate x, y and z coordinates of this position vector of this center of mass. So the separate coordinates of the center of mass can be measured like this. The x coordinate can be measured using the formula capital X as m1 x1 plus m2 x2 plus etc mn xn divided by m1 plus m2 plus etc mn, and using the summation symbol we can write summation over here small n is equal to 1 to capital. It's known, that's why I have not written here. It's understood. Mn xn divided by summation mn. And similarly for y and z, the coordinates become like this: m1 y1 plus m2 y2 plus etc m n yn and divided by m1 plus m2 plus etc mn, and using summation symbol this will become this, and so z will become like this. So these are the x, y and z coordinates, z coordinates of the position vector r. So if a rigid body may be considered as a system of closely packed particles having continuous distribution of mass. So if you are considering a rigid body, the particles inside such a rigid body is distributed continuously without any gap between them. So the distribution can be considered as continuous. In such a case, the center of mass of such a body will be given on replacing the sign of summation by the sign of integration. So we are considering the summation symbol for a discrete system, and if it is a continuous system we can replace the summation by integration. So in a rigid body, usually this rigid body system, the particles will be distributed in a continuous manner. So here the summation index can be replaced by integration. So the x coordinate can be replaced by in the x, y, z coordinates, the summation symbols are replaced by integrations, and it will become numerator integral x dm. Here look at this equation. This is mn xn by summation over n. Here this summation is replaced by integration, and this summation by integration, and similarly for these two coordinates. So this becomes x as integral x dm by integral dm. So integral dm is nothing but the total mass of the system, so we can write it as 1 by m and integral x dm. So the numerator is same in three cases, which is nothing but capital M, the total mass of the system. So it can be written as 1 by m integral y dm, 1 by m integral z dm. For the bodies of regular geometrical shape, the center of mass is the point about which the body is symmetrical. For example, centers of the sphere, disc, meter stick, etc. are the respective centers of the mass. This is what I explained in the starting itself. That is, the point where the body is symmetric is known as its center of mass. That is the point where you can balance that object by the tip of your finger. That point is known as the center of mass. And this is the method how we measure the position vector or the exact point where the body is symmetrical and the point of center of mass occurs. So this is about center of mass. So now we will discuss about the motion of the center of mass. So we have the equation of the coordinate, center of mass coordinate as mr as m1r1 plus m2r2 plus etc. mnrn. From this we will get r. Okay. If we differentiate this equation with respect to time, what we will get? Differentiate both sides with respect to time. So mass is the total mass of the system which is constant, and the position vector of each part of this system is differentiating with respect to t. So if we are differentiating, this equation will become like this. dr1 since r is the position vector, the differentiation with respect to time will give you the velocity. So this dr by dt is m into v. So which is equal to m1 v1 plus m2 v2 plus etc. mn vn. Where v is the velocity of the center of mass, capital V, and v1 v2 etc. are the velocities of individual particles or masses present in the system. So capital MV can be written as summation over Mn Vn. Okay. So MV is nothing but the product of mass into velocity, which is momentum. So we can represent it as momentum. Okay. So from this V can be written as summation over Mn Vn divided by capital M. So this is m1 v1 plus m2 v2 plus etc. mn vn divided by m1 plus m2 plus etc. m into n mn. So this equation gives the velocity of the center of mass. So from this is the velocity of center of mass. So from this we got the velocity of the center of mass. The RHS of the equation, this equation is the total linear momentum of the system, and it is equal to the product of the total mass and the velocity of the center of mass. So the total linear momentum of the system is the total mass and the total mass and velocity of the center of mass. In the absence of external forces, the total linear momentum remains constant. Hence we can write capital MV is constant or V is a constant. So from this equation we have got capital MV is like this. So this belongs to the center of mass. So this is the linear momentum of center of mass. Okay, where M is the center of mass, total mass, and V is the velocity of the center of mass. So according to law of conservation of linear momentum, in the absence of external forces, the linear momentum remains constant. So if linear momentum remains constant from this equation, that means mv is equal to constant, or v is a constant, velocity is a constant. M is already a constant, so v is a constant here. This is a remarkable property of the center of mass, that its velocity remains constant in the absence of external forces. For example, when a radioactive nucleus moving with constant velocity decays into a number of particles, the particles moves in different directions with different velocities, but the velocity of their center of mass remains the same. However, if initially the center of mass is at rest, it will remain at the same position afterwards. So this is just a demonstration of the velocity, the constancy of velocity due to the absence of external forces. That's what is depicted here. That is, in the case of a radioactive nucleus moving with a constant velocity, when it is decays into number of particles which can move move in different directions with different velocities, but the center of velocity remains, center of mass velocity remains the same. That's what is described here. It is an example. If we differentiate the center of mass momentum equation with respect to time, we get, so we have got the equation P as m into capital V, and if we differentiate with respect to time again, we will get dp by dt as m into dv by dt, which is again d by dt of m into v, which is the representation of m into v. So this is nothing but the force according to Newton's second law. Okay, where Fn is the force acting on any particle n of the system. Hence the total force, which is summation over n Fn on all the particles of the system, will be equal to the external force, which is represented by F suffix external. Because taking all the particles of the system, the forces of their mutual interaction cancel together according to Newton's third law. So total external force is equal to dp by dt, which is equal to m into dv by dt, which is equal to m into a suffix c, which represents the acceleration of the center of mass. So we have got the equation for force also. What we have done is we have differentiated the linear momentum equation with respect to t, and we have got the expression for force. Since m into dv by dt will represent the acceleration, and the rate of change of momentum will give you the equation of force, and the right side will give you the total forces of the total sum of the individual forces, and the left side will give you the total external forces, which is the force acting on the center of mass. The acceleration of center of mass is due to only external forces and is given by Newton's second law of motion. So inside the body, there can be interaction between individual particles or masses, or the forces may be acting between particles inside the system, but according to Newton's third law of motion, that forces may cancel each other, because every force may be equal and opposite in action, so they may cancel each other according to Newton's third law. So the total force may be completely due to the external force acting on the system. Thus the center of the mass of the system of particles moves as if it were a particle of mass equal to the total mass of the system, subjected to the external forces applied to the system. So what we have got from this equation is F external is equal to mass into acceleration of the center of mass. So what this equation says is that the center of mass of the system of particles moves as if it were a particle of mass equal to the total mass of the system, subjected to external forces applied to the system. So we are not, this equation tells nothing about the internal forces, because the sum of all the internal forces is cancelling each other. Okay, so the effective force is external forces only, and the motion is like the motion of the center of mass as a total mass of the system. So this is about the motion of the center of mass. Now we'll talk about center of mass frame of reference. So we know now what is center of mass. So what is center of mass? Frame of reference. A frame attached with the center of mass of an isolated system. That is a system which is free from external forces. Such systems are known as isolated system. And a frame attached with the center of mass is known as the center of mass frame of reference, or simply C frame of reference. Sorry. In this C frame of reference, the center of mass remains at rest, that is, V is equal to 0. So in this C frame of reference, the center of mass remains at rest, so that the velocity is equal to 0. So that from the equation mv is equal to mn vn, which is equal to p, that is the linear momentum equation, it is clear that the total linear momentum of the system in C frame of reference is always 0. So the center of mass, in the center of mass frame of reference, the velocity is 0, so that the linear momentum is 0, which means P is equal to mv is 0 in C frame of reference. Note this. For this reason, the C frame is also called the zero momentum frame. Such a frame is sometimes very much convenient for the analysis of many experiments which are difficult to be analyzed in the laboratory system. So in the C frame of reference, the linear momentum is 0. So that C frame is also called zero momentum frame. Zero momentum frame. And such a frame is very important because many experiments can be analyzed which are difficult to analyze in the laboratory systems. So C frame of reference is called zero momentum frame of reference. The center of mass of a system in absence of external forces moves with constant velocity is an initial frame. So the center of mass of frame of reference for the isolated system is an inertial frame. So the center of mass of system in the absence of external forces moves with a constant velocity. And so in the absence of external forces, center of mass frame of reference moves with a constant velocity. So then it is known as inertial frame. For a system of particles which is acted by external forces, the C frame becomes accelerated, that is non-inertial, and it is not of much use. So when it is acted upon by an external force, it will become accelerated, and it is known as then a non-inertial frame of reference. So this about the concept of center of mass, the motion of the center of mass, and the center of mass frame of reference, etc. Okay.